Hey folks, well, now that we're getting into some more interesting program development, right, we've got the ability to write functions now, we've got the ability to use recursion now, we've got the ability to use ifs and else statements or switches, and pretty soon we're going to be getting into the use of loops. So we're starting to get into areas where the debugging problems are going to become a little bit more complex. And so I want to take a few minutes now to just give some advice on good habits to get into for debugging and for writing your code so that it'll be easier to debug. So that's kind of where I want to go today. Again, debugging is pretty much an inevitable part of software development, right? When you're writing a large piece of software, it gets complex. Your first versions are going to have bugs. And if it's really complex, then the odds are even your late versions are going to have bugs, and there are going to be things that you don't find out about for quite some time. So you've got to be able to dig into your code, figure out what the problem is, and fix it without breaking anything else. And you also have to be able to test it to make sure that it does actually work. We'll get into the testing side of things in our next session, but for now I want to focus on the debugging side. So probably the first most important thing is to focus on having good coding habits, because that will make it easier to debug when we get there, right? If we're writing kind of garbagey code, it is much more difficult to wade through that and figure out problems later. So we want to go through and follow a good kind of top-down design process where we're taking a program and coming up with a structured solution where we're saying, okay, this program has these three big steps. I'm going to have one function that focuses on the first step, one function that focuses on the second, and one function that focuses on the third. My main routine is just going to kind of call those three and exchange whatever variables are needed to communicate between them. But it allows us to focus on one piece of the problem at a time. And the same thing comes in with the debugging, right? If the debugging is related to the first task, then we're just focused on that one section of the program. It lets us split things up into manageable pieces. The other thing that really helps is following the code standards, right? Right from the moment you start writing a program, write it to adhere to the code standards. So as you're writing it, use good names. As you're writing it, insert good comments. As you're writing it, follow the indentation and layout rules, so that right from the beginning, your code is clear to read and clear to follow. And the thing is, most of your debugging, the worst of your debugging is in the beginning, and then gradually as your program gets better and better and better, you have fewer and fewer debugging issues because you're ironing them out as you go. So the time when you need clear, easy to read code the most is right at the beginning. So I've seen a lot of people who go through and kind of write their code in sort of a haphazard mash, and then at the end go through and try and clean it up and say, oh, well, Dave says we've got to follow the standards, so now I'll go put in the indentation and put in the names and get it all right that way. That means that you're losing most of the benefit of having clean code, because while you were going through debugging, you were having to wade through this stuff that's difficult to read and difficult to follow. As we get into this, if you bring your code to me for help debugging, if your code's a mess, I'm going to tell you to go clean it up and follow the code standards first, and then I'll take a look at it once it's cleaned up. Because it's a waste of brain power to try and weed through poorly laid out code. So follow the code standards right from the moment you start writing a program. And then the other thing that helps a lot is the idea of iterative development that I've harped on a bunch of times now, where essentially we want to go through and get one small piece of the program written and working at a time, right? Add one chunk of code, get that to compile and to work, and then move on and add the next. And again, this means that when we're debugging, the problems we're encountering are pretty likely related to, if they're not actually in the chunk of code we just added, they're closely related to the chunk of code we just added. So it does help, again, narrow down the scope of what we have to weed through to find where the problem actually lies. So good habits in coding are one of the most important things in making our debugging easier. And then the other things I want to get into, And again, we'll talk about the testing side in our next session, but good testing skills are important to allow us to actually find the problem, to identify that there is a problem and what the nature of it might be. But we want to look today in particular at the skills that will help us during the debugging process itself. And then we'll take a quick look at debugging tools and how those can help us as well. All right, again, I pretty much just ran through all this, but following the code standards as you write is going to help you during the debugging process. Using iterative development is going to help you during the debugging process. A couple of other things to keep in mind are don't make your code needlessly complex. Don't use fancy weird tricks to just try and shorten a line of code by a few symbols or to cut out one line of code in your program, because it makes it harder to read, harder to maintain, and harder to debug. It might be clever and cool, but in the long run, you're going to pay a price for it. And the other thing is, if you've got a complicated expression, break it up into smaller, manageable pieces. Store intermediate results in variables and use the variables later in the expression. Again, because the more complex it is, the more difficult it is to read it and follow it, and the more likely it is that there'll be, a typo or a glitch somewhere in there that's hard to find. In terms of just kind of a few common sense bits and pieces that really do help, the first thing in debugging is to make sure that you understand the circumstances under which the problem is cropping up. So if you think there's a problem, see if you can come up with a way to consistently reproduce it, right? What data values can I use? What sequence of steps can I use when I'm running the program to make the bug happen? And that will help you. If you can narrow down when the bug does happen and when it doesn't happen, then that's going to help as we're actually going through the code to figure out where the problem might lie. Another big thing is to focus on just one problem at a time, right? Don't try and don't try and solve a whole bunch of different bugs all at once. Focus on one of them. And it's important if this is sort of compiler focused, if you compile a program and it produces 50 compilation errors, don't try and solve the later ones first. Focus on the first message, the first error message it spews out. Because what often happens is the compiler hits that first bug and it gets confused about what's going on in your program because there's syntax errors in there, and so it doesn't understand the grammar that you're using. And so the later messages might be complete gibberish because the compiler's already been confused by whatever that first bug was. So you have to solve the first bug in the list first and then move on to the others. You might find that solving that one actually gets rid of 90% of the rest of the error messages you see. In terms of, lots of times when you hit a bug, it's going to be pretty obvious. You're going to, oh, right, okay, I've got a typo there, or I've missed a semicolon here, or whatever it might be. But there are times when you run into logic problems where it gets really difficult to figure out, why on earth is it doing this? And one of the things that really helps is explaining the problem to somebody else, anybody else. Explain it to me, explain it to a lab instructor, explain it to your buddy, explain it to your cat. It doesn't matter who, because what happens is as you're trying to explain the problem to someone, you're forced to kind of think through logically what you need to tell them, the steps you need to tell them for it to make sense. And often this organizes the problem better in your own head, and suddenly, as you're halfway through explaining it, you go, oh, I know what's going on, and you can solve the problem. Other things that will help, get somebody else, get a fresh set of eyes to look at the code. Sometimes there's a syntax error that's in there that you just can't see, right? Because you typed it, you know what you meant to type, and when you're looking at it, your eyes kind of glaze over and go, oh, I know that, I know that, I know that, that's supposed to be this and this and this and this, and you don't see a simple typo in there someplace. So getting someone else to take a look at it is often a good aid. If you've been hacking away at a problem for a while, again, I strongly recommend taking a break. Go outside, walk around, have a coffee, take a shower, take a nap, whatever it might be, take a break, and then come back later with fresh eyes. Because often, you've been staring at the problem for an hour or 2 hours or whatever it might be, and you're just not spotting anything new. You go away, come back with kind of a fresh outlook, open it up, and almost right away you'll often go, oh, geez, there it is. Why didn't I see that earlier? But it is a fairly common thing to have happen for us, for everybody that does a lot of debugging. The other thing I'll mention is it's useful to learn to use a debugging tool effectively. These are programs that allow us to examine our program as it runs and to examine our code as it's executing. And we'll take a few minutes to talk about that in a little bit here. It helps, and one of the things that you'll find over the course of time is you get accustomed to seeing certain kinds of error message and you go, oh, that's probably because of something like this. So you get to learn the kind of cause and effect, what kinds of programming bugs tend to lead to which kinds of error messages. So a lot of that comes down to experience. Again, just as a few examples here, if you get an error message that's a stack overflow, or at this point in the programs we're writing, if we get something that's a segmentation fault, quite often those will come from just runaway recursion, where we get infinite recursion taking place. So we've missed a base case somewhere. Or sometimes, as we'll get into arrays and pointers and things later on, those will lead to segment errors that crop up. Segmentation fault in the program just crashes. So the error messages you get aren't always very intuitive, and if the program just says segmentation fault, that for most of us doesn't tend to imply anything naturally, but you get to learn the kinds of things that cause those problems. Things that you're probably running into already or have run into already are, the compiler complains about some variable isn't declared in the current scope, or some function isn't declared. It might simply be a typo, where you've misspelled the name of the function or the name of the variable where you declared it, or where you were trying to use it. So take a look at the place where you declared it and take a look at the place where you've used it, and just make sure that the two names are actually typed exactly the same. So yeah, typos are pretty common, or simply forgetting to declare a variable, or forgetting to put in the prototype for a function, or putting them in the wrong place. Again, those are all pretty common. If you're doing some output and you're getting kind of really weird values or large values, you're printing out something you expect to be like a 10 or a 12, and it's coming out negative 3,876,004, then quite often this will be related to either input and output issues, or forgetting to return a value from a function, or for using uninitialized variables and you're getting this kind of random uninitialized value from the beginning. So again, things that wind up becoming fairly common and you get used to looking for. A lot of typos are pretty common. We're all typing lots and lots and lots of code, and it's easy to mistype something. Common things like we've mentioned with comparisons, if you're trying to check if two things are equal, if you want to see if x is equal to y, that has to be the two equal signs to do the comparison. If you just do one equal sign, it thinks you're doing assignment. And so it's really easy in the course of your code to accidentally put two equals where you mean to assign a value, or to put one equals where you mean to compare values. So again, things like this are common errors that you get used to looking for. And you also get used to looking for these errors when you're helping somebody else, taking a look at their code, saying, oh, look, don't you want two equal signs there? Or, don't you only want one equal sign there? And one of the big things is, don't just kind of blindly stare at your code and hope that an error is going to leap out at you. See if you can learn to look at the nature of the bug, whether it's a compiler message or whether it's behavior that you're getting when the thing runs, and come up with a theory or a bunch of theories on, well, what might be causing that? And the more you do this, the more you think, well, what might be causing this problem? And then digging into the code and trying to verify that, it helps you learn about what types of things really do cause the problems. Right? You'll get better and better at debugging if you follow this kind of an idea of stopping before you dive into the code and thinking about, okay, what's likely to be the source of that problem? And so once you've come up with a theory on, or a couple of theories on what it might be, then stop and think, okay, well, how could I figure out if that's actually the problem? Sometimes it's obvious. It's like, okay, well, if I think that I'm getting an assignment where I meant to do a comparison, I can go in and look for an equals versus double equals or something along those lines. So sometimes it's simply a matter of, oh, well, this one's probably a typo, or this one's probably a forgotten declaration, or this one's probably a forgotten initialization. And so you just open up the code and look to see if that genuinely is the problem. But sometimes you'll go through and say, well, what are other things that I can check? Maybe if I've got some incorrect result coming out during my computation, maybe there's a problem in my logic formulas, the way I've actually structured my equations. And so you can start, maybe we throw in an extra printf or cout statement somewhere in the middle to look at the values that it's computing kind of halfway through the process and see if it seems to be getting the right value. So come up with a test case, think about what the values should be, and then throw in some print statements to see if that's what the values really are. And you can start narrowing down what might be going on. Or if you think, function A is supposed to be calling function B, is supposed to be calling function C, and when it gets there it should do this, you can throw in statements to say, okay, well, let's see if it really does call function A, which really does call function B, which really does call function C. If you discover that it calls function A and then function A just ends and it doesn't call the other ones, then you've got more information about what's going on. So this idea of coming up with a hypothesis and following through on it can be really handy. All right, in terms of tools to support this, debuggers can be a really handy way to go because they allow us to examine what's happening in our program as it runs. So the one I'm going to take a look at here is simply GDB. It's the debugger for sort of C and C++ and a few other languages on our servers. It's a text-based one. There's also a graphical version called DDD that still has GDB under the hood, but it gives you a nicer kind of visual interface. To use this, it's going to, again, allow us to examine our code as it runs, but for that to work, the compiler has to stick some extra information into the executable. So we have to throw an extra flag in when we compile the program. So let's say I've got myprog.cpp and I want to compile it and then use the debugger on it. So I'm going to create my executable called myprogx, and so I'll use my usual, G++, myprog.cpp, the -o, the executable I want to create. I'll use my usual warning flags, but I'm going to stick in this -g. And this is the one that puts extra information in so that the debugger can work on the executable. After that, we'll use GDB and run it on the executable, and this will allow us to analyze it as it runs. So when you do this, GDB will spew out a bunch of information, kind of about the program itself, and then it'll fire up and wait for you to type debugging commands. So let me just show you what that actually looks like. So here I've got a program called points.cpp and an executable points, right? So I go through and use my, if we wanted to compile, again, the idea would be I want to compile points.cpp, I want to create an executable named points, I want to use the -g debugger flag, and I want to use my warnings. So I compile it, and hopefully it compiles okay, and then I'll run GDB on that executable. And again, it gives me this big blurb about licensing information and blah, 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 blah. And then eventually down at the end there, you see it pops up this GDB prompt. So it's waiting for me to type in GDB commands. So I can simply quit if I want to and get out of the debugger and get back to the beginning. Or we can start running some actual debugger commands. So we'll look at those first and then we'll try them out in the tool here. So again, as I just showed you, quit will exit the debugger. We can just run the program in the debugger using the run command. If the program crashes, so if the bug you're trying to track down is that the program crashes with like a stack overflow or a segmentation fault or something like that, then we can type in a command called backtrace, and that will show you where it was in the program, which line and which function calls it was in at the point when it crashed, which again can be useful debugging information. And we'll take a look at backtrace in just a second. And then a few other things that we can do are, usually we've got some kind of an idea about where we think the bug is likely to be. It's in some, I think it's in whatever function foo. And so what I'll do is tell the debugger to run the program up until it hits that function, and then stop and wait for me to give more commands. And so when we get there, I'll be able to look at the values that are in the variables or in the parameters. I'll be able to kind of run it one instruction at a time and say, okay, run one more instruction and see what it's doing. Run one more instruction and look at the variables. Run one more instruction and look at the variables and see if I can figure out where it's going wrong. So we can, to tell the program where to stop, it's called setting breakpoints, setting points to break execution, to pause execution. And so you can either use break and then the name of the function you want it to stop in, or break and which line in the program you want it to stop on. And again, it'll run normally until it hits that point, and then it'll stop, tell you where it is, and wait for you to type in more commands. And again, once we get there, we can either kind of what's called single stepping through the code, where I can just say, okay, run one more statement, run one more statement, run one more statement. So S, or step, is the command to run one more statement. If it hits a function call and you're using step, it'll try and go into that function and start single stepping through that. Sometimes that's what you want. Sometimes you just want to say, okay, well, make the function call, come back, and I'll continue single stepping in the function that I'm in. So if you use N or next, then it actually treats a function call as just kind of one statement. So it doesn't try and dive in and single step through the insides of it. And if you ever get to the point where you're saying, okay, I'm past the point I'm interested in, just resume running normally, you can use C or continue, and it'll just pick up and run normally until the next time it hits a breakpoint, or until it gets to the end of the program. And again, when we stop, we can take a look at the values in variables using P or print, so px to take a look at what's in X. And using these, we can start exploring what's happening in our program. Now again, this is just a quick intro to a debugger. There are lots of other debuggers available and a lot more detail on GDB in particular. I've got some more information available in the 265 slides and videos if you want to have a look at those, or again, do a Google for more information on GDB in general, or whatever your debugger of choice happens to be. So I just want to have a little bit of a play with that points program and GDB. Actually, I'm going to quit here first so that we can take a look inside the .cpp so we can see kind of what's in there. So in this particular program, I've written a program where the user enters the coordinates for two different points, two different sort of sets of XY coordinates, and it just figures out how far apart the 2 points are. So to do that, it's got one function that just gets an integer from the user. And if the user types in something that's not an integer, it prompts them to try again and try again and try again until they do give something that's an integer. I've got a get coordinates function that gets an integer for X and an integer for Y. So this get coordinates essentially calls get integer twice, once for X and once for Y. I've got a function to go through, and once I've got 2 points, so I've got the XY coordinates for the first point and the XY coordinates for the second, it computes how far apart they are. And then the main routine is essentially just going through and saying, okay, well, have variables for the 2 points, get the coordinates for the first point, get the coordinates for the second point, and that in turn goes off and calls get integer to get the X's and the Y's. Compute the distance, store it in a variable, and then print out the distance. All right, so I've got these 3 functions in the main routine. The get integer is following that kind of recursive process that we've looked at, where it prompts the user, reads in a value, checks if it fails, clears the input if it failed because they typed in garbage, right? They typed in something that was not an integer. And if it does fail, then it goes off and makes a recursive call to try again and stores that in our variable. Right, eventually that get integer call is going to go off and recurse and recurse and recurse and recurse and recurse and eventually give us back a valid value, which we're storing. And then down at the bottom, we'll simply return that valid value. All right, so this is pretty much the kind of approach we've been looking at so far. The get coordinates is just calling get integer twice, once for X, once for Y. And the computing the distance is just doing our distance between 2 points formula, where we take the square of x2 minus x1 plus the square of y2 minus y1 and take the square root of that sum. So that's the idea for the program, but we've got this get coordinates routine, the distance routine, and the get integer routine. So what we'll do, and we've got a coord variable inside that get integer, let's take a look at our program. Again, we'll try running it through GDB. I'm going to set a breakpoint to stop in get integer. And now I'm going to say run, and it's going to run up until it hits that get integer. So it should get into the get coordinates for the first point, where it's asking for the x coordinate, and then it'll hit this get integer routine and pause. Right, so the program runs normally until it hits that get integer routine. It pauses and tells me where it is. Right, it tells me that it's at get integer, and it tells me which line of the file it's in and which statement that is. So we've hit the point where it's asking me for that first integer for x. Right, so we saw this output from the program. Right, getting coordinates for a point, x value first. Please enter an integer. So I'll do a single step here, or let's do a next here. Right, so I see the output from the program where it actually runs that cout, tells me to please enter an integer, and so now we're at this cin statement. So let's do another next. And so now it's actually running the cin, and so that cin is waiting for me to type in something. So I type in 12. And so the program is now going to run that. It's stored the 12 in the variable. So if we try printing out coord, then we see, yeah, the 12 wound up in my coordinate variable. And so, again, now I'm just going to say let's continue until the next time we hit a get integer, which will be the same idea for y. Right, so now we've seen the output, it's asking to get the y value, and it tells us where we are in the program. So you can go through and see what's going on. And again, if we try that backtrace, it shows me that I'm in get integer, which was called from get coords, which was called from main. And it gives me a whole bunch of other information that we'll ignore for now. But it does show me where we are in this call sequence. All right, that was essentially the kind of quickie intro I wanted to give you for our debugger. I will let you play with that at your leisure. And if I go through and ask to quit, well, I've still got a program running. It just prompts me to make sure I really want to do that, and I do. So we'll get out of here. But again, a quick intro to GDB. All right, I will leave that there for now.